Hi, everybody. My name is Marco Patrignani. I'm a professor at the University of Trento, as you can tell, because I don't look anything like my profile picture. And when I'm done updating all my profile pictures, I would like to do some research on blame-preserving compilation, which is some ideas I had with my student Matthis, who is over there, right? And as I've learned from the more senior in the crowd in previous PriSC, if some of the ideas you hear are that look appealing to you and want to work on them with us, come. We have openings at both the University of Trento and CISPA to work with us on these things. So come, yeah, that's it. So unlike some of the very nice, more mature work that we have seen so far, this is not very mature. This is a bunch of ideas that I came here to discuss because, as we've seen in previous year, PriSC is a very lively audience, made of very, very good researchers. So it's a very nice place to soundboard your ideas. So um, keep it up. And what I hope to do is to convince you that what we're looking at is an important foundational problem. So like, we're gonna essentially take a look at how to extend the fundamental theory of secure compilation. And as for other talks, please ask questions, interrupt me if there are things that are imprecise or unclear. And if things are interesting, come talk to me afterwards. Just know that I have a plane to catch. So I want infinite time. So let's start with the background from far away. So we have whole program compiler correctness a la compcert, which states that a compiler is correct, assuming that a source whole program W satisfies P. Then we need to prove that its whole program compiled counterpart satisfies the same property P, right? And we have whole programs. We have satisfaction, which means that for any trace T that the whole program does, then the trace T is in the property P. And here you notice that the satisfaction is colored, so the satisfaction is up to the language in which the program is written. We have source programs that follow the source semantics written in blue, and the target programs that follow the target semantics. Now, for now, you can, when we talk about satisfaction, indeed, we talk about programs emitting traces, and for now, we leave it as an abstract trace model, but just know that later on, we'll need to impose some constraints on the trace model. And if you're not familiar with what should I think this trace model to be, a common abstraction that works is you could think about it as like I/O interactions, like your source and compiled counterpart. What kind of I/O calls do they make? Although we'll also need to specify this further for the problem we're interested in. Now, the issue with compcert style definition is it has no explicit notion of security. Therefore, some years ago, we did the robust compilation framework that whose diagram has been displayed in the previous session. And we can say that a compiler attains robust compilation for some class of property P if the source component, if any source component robustly satisfies the property, then its compiled counterpart also robustly satisfies the same property. And now the changing gears to introduce security, you see that we are now talking about components C, which are partial programs that replace what we had previously that were whole programs, and we have robust property satisfaction. And what is it? You might say, well, robust property satisfaction is indeed stated in terms of components. When do components robustly satisfy a property? When they satisfy the property for any program context that they are linked with. So in this case, we are dealing with the partial programs. How do we go back to the whole program setting? We close the partial program off, quantifying over all possible other larger programs that can interact with said component, okay? And this is what gives the security edge to the definition I gave you, because now these program contexts are the attackers in the picture. And you might be wondering, as happened the other day when Anita was talking about robust safety for assembly, like, is this actually a meaningful and attainable thing to do to prove properties robustly? And I would say yes, there is quite a bit of literature on the subject. There's many works on robust safety that we have seen for protocol verification around the 2010s, and more later on by Michel. Are you here? Yeah. his good work, and so at the language level, and there's also, sorry, at the program level, and there's also language level robust property satisfaction, such as the work on memory safe WebAssembly that Anita's presented a few days ago. So this is not unheard of as a property to aim for. And why do we want to deal with robust compilation instead of, say, for example, the elephant in the room, like full abstraction? The good things about robust compilation is that it is intentional in the security definition. Having to deal with the traces means that you have to express at the trace model what is of interest and what is not of interest for the security property. Therefore, yeah, you get a clear characterization of what matters and what does not matter for security. Moreover, the robust compilation work is general over classes of properties. So if you're interested in safety, hyper safety, general hyper properties and such, there are criteria that work for them. And it's compositional. So if you have compiler 1 and compiler 2 that are robustly, that attain RC for a certain class of property, then you can compose the compilers and you still attain the same class of property. And as my student Matthis is studying, this composition works really well for different forms of composition of compilers and for different classes of security property that the compilers that are being composed attain. So, okay, let's unfold a bit RC to understand the only unfortunate thing that I could find in this. So a compiler attains RC if for all, so when I unfold the definition of robust satisfaction, given that for all source context, the context with the component satisfies P, then it's then for all target context, the target context with the compiled component must satisfy the same property, right? And here we see again that, well, the security aspect that comes into play, because we have the target attacker, the target context K, which is the attacker to the system. What needs to be secured is the component being compiled. And what does it mean for the component to be secured? It means that after compilation, it must still satisfy the property of interest, right? But there is a problem with this definition, okay? And the problem is, to cut to the chase, that the premise can be false. And with a false premise, we suddenly get a criterion that is trivially true, and it accepts too many solutions, right? And what does it mean for the premise to be false? Well, let me give you an example. Let's consider a compilation from C to Rust, a compiler from C to Rust, and this compiler we want to prove that it to be temporally memory safe. Okay, so essentially we want to prove that if the source is robustly temporally memory safe, then the target is robustly temporally memory safe. And this should be, I mean, if we have our usual secure compilation hat off, knowing that we're compiling to Rust, we know we have everything in our power to attain robust memory safety of compiled code, right? That's what the Rust type system gives us, especially if we're talking about safe Rust, right? But there is a problem. Let's consider a C component interacting with a C context. Our function starts executing. It might allocate 3 memory regions. It gives control back to the context, which allocates some more memory regions. But the context, what does it do? Well, it does some pointer arithmetic, goes back to the previous regions allocated by the component and frees them, right? And it tampers with what the component had done. And when the execution goes back to the component might, well, free them again, triggering a temporal memory safety violation, right? And this would be essentially like when we take a look at the trace that gets produced by this example, we see, well, there's the allocation of the 0 to 2 memory, allocation 5 to 7, and then there's twice a free of the 0 to 2 memory region. But intuitively we see, well, this is not a problem with our component, right? This is a problem with the context. It was the context fault that now we get a violation of temporal memory safety because the nasty context freed our memory. It shouldn't have any business doing that, right? And the problem with this kind of approach is that we see that there are a number of research works developing target languages for secure compilation that provide strong security guarantees. We have memory safe WebAssembly, we have Rust, we have Morello. And when you get a compiler from an insecure language down to a secure one, well, any compiler can fulfill the robust compilation state criteria that I told you before, because the premise is trivially false, right? So now your statement is imprecise, and it doesn't really help you in proving that you had the right compiler, like the right compiler to begin with. It accepts too many compilers, right? And the solution that we want to study to address specifically this issue is called blame-preserving compilation. So which would be a sort of a novel criterion that is inspired by either by the robust compilation set line of work that would essentially let us compile from insecure to secure languages. And as I was telling you in the C example before, the issue here is that the issue that we had before was that it was the context that screwed up with our memory, right? We could reconduce the fault in the temporal memory violation into some action done by the context. And this is where this idea of blame came into the discussion, right? Just to familiarize the audience with the notion of blame, blame is a notion that arose as a follow-up to sort of gradual typing. I wish Aimal were in the room because I could ask her to stand up and tell it to you guys. But essentially, in blame calculi, you have both a typed and an untyped part. And there, of course, you cannot say that your program, like well-typed programs, can't go wrong because it's not all well-typed. What you can say is that if anything goes wrong, it's the untyped code's fault, right? And we see that parallelism in here because, well, the temporal memory violation that we saw, it was exactly just the context fault, right? So perhaps what our line of reasoning is, we should be able to bring some of the blame ideas into the secure compilation setting. So what this boils down to is, if we could identify, we would first need to identify which entity does an action. And in my experience, I think at least, let's say most, just to stay on the safe side, most secure compilation work have something in place that whenever they are dealing with actions and traces, you can always identify who did the action, right? It's always essentially there's always two parties involved, the context and the component. And in all the formal development, there's always something there that can tell you, that can help you tell who did this action. You can always tell it's the context or the component. And so we can label the actions that build the trace accordingly as belonging to the context or to the component. And with this, we can devise like blame membership. So what does it mean for a trace to be in a property in a blameful way? And one definition that could work is something like this. A trace is in a property blamefully if it can be split into parts. The first one which satisfies the property, and the second one that starts with a context-made action that violates the property. And for those of you that are more experienced with the categorization of security properties into safety, hypersafety, and such, this reeks of safety properties because, well, we start talking about finite traces and prefixes and such. And indeed, insofar, I had not pinned down what kind of classes we're interested in, but I think safety should be a good first start. And there's a lot of security properties that can be characterized as safety properties. And I would be happy if we could have just blame-preserving compilation for safety properties, okay? But most likely it would work for hypersafety as well. But just so you know, prefixes and safety-like things. And when we look at the trace here at the bottom, the trace that violated the previous example, we can easily identify the fact that, well, the first allocation was done by the component, then there's the second allocation done by the context, the first free done by the context, and the final free done by the component. And it's exactly this action, the one that was done by the context, that is violating temporal memory safety. And so this trace, now it would satisfy the property of being in the property of temporal memory safety blamefully, right? So yes. That's a very good point. Um, the I didn't want to throw too many technical details in here, but what I believe we could do here is the way the first free is is defined as the one violating the property is because that was done doing some pointer arithmetic, right? So how can the context come and free our memory? Well, we didn't give any pointer to it, so the context crafts a pointer to our memory, and that's the thing that effectively kind of reveals a violation and then frees some memory that it didn't really have control over, right? Sorry, what can you? Yes, exactly. Yes, very good point. Yes, but there's existing work on this, like on pointer provenance kind of annotations. So, but yes, that would be the point. But if I started talking about pointer provenance and everything, I would need 2 talk slots to talk about everything. So, but apologies for the imprecision. Is it more clear now why I believe we can reconduce this to a fault in the context? All right. So with this notion of blame, we can essentially put it into all the previous definition and obtain blame version of the previous definitions. Instead of having property satisfaction, we can have blame property satisfaction. Instead of having robust blame satisfaction, instead of having robust satisfaction, we have robust blame satisfaction, and this just boils down to using essentially instead of the trace belonging to a property, using the trace belonging blamefully to a property. And when we do this change up to the compiler, to the robust compilation definition, we would obtain something that we call blame-preserving compilation that looks like this. So if a compiler attains blame-preserving compilation, assuming that the source robustly blame satisfies the property, the target also robustly blame satisfies the property. And this, when we take a look at our C2Rust example, this is no longer a trivial statement, right? Because now our premise is no longer false, right? And or at least that's the hope. And which means that we have now a statement for a secure compiler that is more precise. And in order to show that a compiler preserves the property, in the case of the example, the temporal memory safety from C2Rust robustly, now we have to essentially reason about what is the compiler doing at the target. Okay, so we have narrowed down the class of admitted compilers for showing security. Okay, and where it would so. But then the second issue that generally arises when defining new secure compilation criteria is, well, when we stay at this level of preservation of properties, there is a bit of a disconnect between source and the target actions. Right? After all, we have the source doing a trace that is in the property, and the target doing a trace that is in the property, but there is no, like, the 2 traces are quantified differently, right? And this can be a problem because there can be at least a disconnect between what the source program did and what the compiler can do. And so now enters some bits of text that are probably wrong. So this unclear source to target connection between what the program does in the source and what the compiler does in the target generally is addressed with the devising of an additional definition that ties the execution done at the target with the execution done at the source, and proving that the 2 definitions are equivalent. And now, which is what we've done in the robust compilation work, you end up with 2 criteria for secure compilation. And I would stress that this is generally what you want to do when devising new secure compilation criteria, because the former one, the BPC, the one that was in this slide, gives you a very precise characterization of security. When you read it, you understand clearly what kind of security properties is my compiler preserving. Where is its focus? When you try to prove this stuff, this is not what you want to do. Instead, what you want to do for example, proofs, you want to use these kind of statements because they are, well, there you can use all the nice proof techniques that many people have worked on, okay, like back translation, etc. And I would, and essentially you get the best of both worlds. You get something that has precise security guarantees and that is provable. Okay, so I mean the two keys, I think, is the two criteria is quite important for secure compilation statements. Right, so I hope to have convinced you that at least this should be an interesting problem to look at, but you might have some reserve onto whether the solution I'm bringing forward is actually the right solution. Are there alternatives to BPC? Why can't we just prove that the compiler enforces the property at hand, right? Why can't we just prove that the compiler from C to Rust enforces temporal memory safety? You know the answer, Matt. And here we also have another issue, right? Because this is another of those statements that is a bit too lax. It allows for too many solutions. For example, a compiler that generates arbitrary, well-typed, safe Rust code robustly satisfies temporal memory safety. Do we want to accept the compiler that randomly generates code as a good solution for a secure compiler? Arguably not. We can have discussions on this. So there is a loss between what you do in the target and what the semantics that you produce in the target and the semantics that was done in the source. You could weaken robust compilation and consider less context, but please refrain from doing such rational acts. You have the problem with weakening robust compilation and considering less context is that suddenly you have a loss of security. You consider fewer attackers. So why would you want to consider fewer attackers? Well, Matt gave us a very good explanation for that before. When dealing with stuff like robust crypto for cryptographic libraries, you might want to put additional constraints. And I buy that argument. But in general, when devising general criteria, I don't think we should aim for criteria that work for a restricted set of contexts. We should be trying to devise criteria that work for the maximal kind of security applications, because that restriction works for crypto code, but then then comes other kind of code that doesn't fulfill those premises. Or we could use secure compartmentalizing compilation, like the work that Catalin's group have been publishing at CCS in 18. But there are some differences. I would say there's technical differences between what I'm presenting and what Catalin did. They have something specified to undefined behavior that does not trace the fault back to a context. And I like to think about blame-preserving compilation as sort of a generalization of what they had. They had some very nice ideas, and I think, Catalin, correct me if I'm wrong, but I think they also talked about blame in their work. And I think this is essentially generalizing what they had to a larger setting. And if I also remember a conversation with Catalin back in the days, I think their definition there boiled down to robustly safe compilation. And I don't know, as I said, the formulas, some of the formulas I've shown are imprecise. I don't know if blame-preserving compilation, as we are thinking, it also boils down to RSC. It might, but we'll see. But I would like to take questions now, and I'm done. Oh, this is going to be long.
Well, I don't know. I'm pretty confused about what you're trying to do in a way, even like, especially when you talk about C, right? Is that really your case study? Because in C, the program you showed stops much earlier. Freeing someone else's memory is already undefined behavior, and execution will not continue in the source, and no one else's memory will be freed. So in a way, that's not how C works. What you showed on the
sure, but there, yeah, the setup is a bit more general. Like, we want to be able to understand whether, and again, undefined behavior is also the implementation of undefined behavior is not is for various platforms to decide. So some execution some models would allow the
but
continuation.
you are showing your source semantics, right? You want a property that talks in terms of the source semantics. The source semantics of C, you try to free someone else's memory, it's undefined behavior.
Sure, but
there is no other semantics at the
there are
source
models
level.
in which the execution continues, but more generally, I think there are there can be languages in which the violation of the property does not halt the computation right away, right? And then we want to be able to assess the fact that, well, even if the execution continued with the violation of the property, you can still meaningfully talk about the execution happening, like at least the right part of the execution happening at the target.
Can we actually identify blame accurately, like associate it with the context or with the component? Can we? Do you think you have intuition that we could do it?
I think, yeah, I think, well,
at least like just for properties, like let's not even think about hyperproperty.
So blame in general, I think you can want to define it as in, the first violation of a property happens when done by a context-made action. If your question then is, can you always identify who did an action?
Yeah.
For what I've seen in the formal work so far, yes. I am yet to see a secure compilation work with the trace model where you don't know which entity caused the action. And for example, like the memory safety monitor that we have in the MS-WASM work would exactly capture this kind of stuff. Like my hope would be to strengthen the memory, the MS-WASM work by correctly characterizing the kind of security properties that we have there. Because there, for example, we also consider like C to MS-WASM, and it would be a matter of, and MS-WASM traps whenever someone breaks the memory safety property, right? So it would be a matter of identifying, well, in the source, you violated the property, the context violated the property, and in the target, there is a trap.
So the example I'm thinking, and maybe I could be wrong, is that you pass a pointer to a context and say that context increments it out of bounds and then passes back to the component, and component then dereferences. So it's actually the error is with the component.
That's a very good point. Yes, I would argue that in that case, you should have you could have another way to rule out those programs. As in a simple static analysis tool for robust safety will flag that program as probably violating robust safety anyway. So like if you care about an invariant on a pointer, you shouldn't pass that pointer to unsafe code. Like,
yeah,
or at least you can pass it around, but then you cannot have any invariant on that pointer anyway. So, and then there are robust safety analysis work that flag that. But the problem is that the context can still have the power to break your invariants, pointer arithmetic or other like Spectre perhaps, right? And you still want to be able to talk meaningfully about those attacks. But yeah, that's a good point.
Very quick question. Can you go to the fifth slide? I was just trying to understand the notation.
No, the notation is bogus. I mean, as I said, this is about ideas. It's not about like. It's composition of compilers. You compile. I mean, the output of this compiler is fed to the input of this compiler.
Okay, I think so. All people wanted to ask a question, please raise your hand. How many? Wow.
Excellent. That's why I'm here. Can I claim this is a short talk?
Yeah.
And
now we can take only one. So remember, you were the first one, and lots of material for discussion at the
damn.
Hi, this question is probably slightly orthogonal. So I was thinking in terms of non-interference or constant time cryptography. So in that case, so we have written proof such that you have some kind of security guarantees till a declassify comes.
Oh yeah, that's a good bet, right?
So programmer can write declassify wherever he wants and do the type checking and says, "Oh, my compiler says it is good."
Yeah. Yeah. Good. Is anybody aware about the connection between like declassification and blame? If anybody has worked on that stuff, like I think Bazavesh is hinting at a nice parallel. Like you could see declassification as a place to blame, right? That's kind of the untyped code that can be blamed for the violation of no interference. But I'm not aware of any such line of work, I'm afraid. But we have some more senior experts.
what do you do after declassification? And let's say I'm changing something after declassification. I say, okay, now I don't have to say that it's a secret anymore. So what do you change the
Give up on there not being any other security property after that. Okay, you should learn what was intended to be declassified at that point. And that's all you will learn at that point. And furthermore, continuing on, you won't be learning other things unless there's further declassification.
And also the adversary should be able to control whether you declassify.
Yes, please.
Yeah, like we usually give proof of application to the developer.
Okay, thank you for the discussion. Thanks the speaker again.